Are you ready to have your mind blown? You better be sitting down for this because this is really mathematically geeky amazing. The infinite geometric series. Let's just consider a situation here. So we're going to consider the sum of this infinite geometric series. Now let's just do a quick recall on what it means to be infinite geometric series. So first of all, we start with an initial term, 4, and then we add something, add something, add something. That's what makes it a series, is that we're adding up subsequent terms in this sequence of numbers. So we're adding together 4 plus 2 plus 1 plus a half, thus it's a series. And in this case, we're going to sum up, that's why the capital letter S here, we're going to sum up the first n terms. That's how we talk in math about infinitely many. The first n terms implies infinitely many terms. And it is a geometric series because notice what's happening from one term to the next is that there's a common ratio. A common multiplier, if you will. 4 times a half is 2, times a half is 1. Times a half is a half, times a half is a fourth, times an eighth, times a half is an eighth, etc. So in general, we're starting with the number 4 and we're multiplying by a half over and over and over again. Repeated multiplication, thus raised to the power of n. Notice, when n is 0, 1/2 to the 0 power is 1 times 4 is 4. So this is going to be our n equals 0 term, our 0th term. When n equals 1, 1/2 to the 1 is 1/2, times 4 is 2. When n is 2, 1/2 squared, 1/2 times 1/2, 1/4, times 4 is 1, etc., etc., etc. So we could, if we wanted to, collect this into a single statement and say what we're going to do is we're going to sum up from the 0th to the infinitely many terms of this geometric series. And the question is, does the series converge or diverge? Well, let's consider a little Excel spreadsheet and see. So the 0th term is 4. The first term was 2. The second term was 1, etc., etc. Half, fourth, eighth, etc. And what we're doing is we're summing up these terms. So we're saying 4 plus 2 is 6. Plus 1 is 7, plus a half is 7.5, and then 7 3/4, and then. So notice, as this series goes on, we are summing up smaller, we're adding on smaller and smaller and smaller amounts. And so would you think that this infinite geometric series converges to a finite amount? Or do you think it diverges and just keeps getting larger and larger and larger? Well, notice we're only in the 14th, 15th now terms that we're summing up, and I hope you see that the evidence is pretty strong that this series gets closer and closer and closer to, yes, it's 8. Good job. Yes, this thing seems to be converging to 8. Now, let's go back to Excel and see more. I hope you can see this well. I want to actually stay here so I can draw some things. So in general, we are saying start with a term. In our case, we started with 4. But in general, we say a sub 0. This a sub whatever number is the common way in the mathematics community to express the terms of a sequence or series. A sub 1 would be the next term, a sub 2, a sub 3, a sub 4, etc. But a sub 0, the initial term. So in our case, previously, that initial term was 4. And then, to get the next term in the series, we multiply that previous term by a factor of 1/2. But it doesn't have to be 1/2. In general, a factor of r, a common ratio of r. So in our case, it was 4, and then a half times 4, which was 2, and then we multiplied by a half again. Now, when you multiply by, starting with 4, multiply by a half times 4 was 2, and then multiply by a half again, the way to capture that idea is you've now multiplied by a half twice. 1/2 squared. 1/2 squared times that initial 4 would have been the 1. So we start with an initial amount. We get the next term by multiplying by r. We get the next term by multiplying by r again. So now we're at 2r squared. And then r cubed, and then r to the 4th, and then r to the 5th, r to the 6th, r to the 7th, and now remember, we're going to go to infinity and beyond. And so we're just going to keep on going. And here's the thing, though. In theory, before you get to the theoretical last term, because remember, we're going to infinity, so there really is no last term. But before we get to the theoretical last term of this series, you're going to have one less than that. So you're going to have like r to the 9, and then you're going to get to the r to the nth term, theoretically again, that infinite term. Now, n is going to infinity, remember. So all I'm trying to notate here is there is a theoretical last term, and right before it, it's going to be one less. Notice the powers are always one less before it, one less before it, one less before it. So it's just a way to capture this mathematically, is that this is an infinite geometric series that you're looking at. Isn't it a beautiful thing? All right, now we're going to try to find the sum of this. Remember the last case, my example, it looks like the series was converging to 8. So we're trying to generate, in general, how would we determine that? Well, take that and multiply both sides by r. Because you can. I mean, you can. You can do anything you want to both sides. I want to multiply both sides by r. So if I take s sub n and multiply by r, I get r s sub n. And when I take all of this, there it is, and multiply it by r, I get r times all of that. Algebraically, I'm okay. I've done nothing algebraically incorrect. Now you can rewrite that. Remember before we had r times the quantity. Well, let's distribute the r. If you distribute the r, we're now going to have r times that. And then remember before it was r a sub 0. Well, if you multiply by r, you're going to have r squared a sub 0. And before, when we had r squared a sub 0 right there, when you multiply by r, you're going to have r cubed a sub 0. And then r to the 4th, r to the 5th, etc. And then now, when you get to this term, the one right before the last term, you're going to multiply by r. So if you took r to the n minus 1, let's just say like r to the 99th, and multiply by r, you're going to get r to the 100th. You're going to get the next multiplier, the next number of powers, the next exponent, n. And then when you multiply by r on that last term, you're going to get one more multiplier of r, so r to the n plus 1. All right, now, because again we can, we're going to subtract those two. You can take two equations and subtract them. So when you subtract s sub n minus r s sub n, you get s sub n minus r s sub n. But look at this. When you subtract the right side, something kind of good happens. Notice, if I was to subtract a sub 0 minus, no, there's nothing there, so a sub 0 minus 0 is a sub 0. But r a sub 0 minus r a sub 0 is 0. R squared a sub 0 minus r squared a sub 0. R cubed a sub 0, r cubed. Notice, even in here, there's an r to the 5th a sub 0. And even right before r to the n a sub 0, there's an r to the n minus 1 a sub 0. And then r to the n a sub 0. How nice. When you subtract those two equations, s sub n minus r s sub n, what's left is a sub 0 and r to the n plus 1 a sub 0. Sweet! Now you may be wondering, well, great, why are you doing all this? Now remember, the goal was this. The goal is, I want to find the sum of the first n terms of that geometric series. I want to find a nice formula for s sub n. So by some symbolic manipulations, multiplying both sides by r, subtracting the two equations, boom, I get something that, well, I can continue to manipulate and find a formula for S sub n. So here's where we were, S sub n minus S sub n, and it turned out to be this because everything else dropped out. How convenient. All by plan, by the way. It's not like that. Ooh, I can't believe that happened. We actually made it happen that way by subtracting the two equations. But now watch this. If the goal is to get a formula for S sub n, then look, I can factor out S sub n. And when I do, I'm left with 1 minus r. Notice, S sub n times 1 is S sub n. S sub n times r is r times S sub n. So I factor out the S sub n and divide by 1 minus r, and there we go. I now have a nifty little formula that'll find the sum of the first n terms of a geometric series. Look at all I need to know. I need to know the first term. Remember in my case it was 4? I need to know r. Remember in my case it was 1/2? I need to know a sub 1 is 4. That's all I need to know. I need to know two things. I need to know a sub 0, the first term of the series, and I need to know that common multiplier. So in our example, S sub n, the sum of the first term, remember Excel suggested it may be converging to 8. So I take the first term, I add r, raised to the n plus 1 power, raised to the n plus 1 power, all times 4, all divided by 1 minus r. Now remember, we're talking about infinitely many terms. So, sorry about that, crash over there. Infinitely many terms. So if you took 1/2 to the bazillionth power, 1/2 times 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 1/2, if you multiply 1/2 times itself a bazillion times, the result is just something minuscule, practically 0. And if you take something that's practically 0 and multiply it by 4, you get practically 0. So as n goes off to infinity, 1/2 to the n plus 1 power just gets infinitesimally small. So we're left with 4 plus 0 over 1 minus 1/2. We're left with 4 divided by 1/2. Now think about division for a minute. Division says how many 1/2s go into 4. How many times does 1/2 go into 4? 1/2 and 1/2. There's 1. 1/2 and 1/2. There's 2. 1/2 and 1/2. There's 3. 1/2 1/2. There's 4. 8. There's 8 1/2s in 4. And so sure enough, this formula works nice. But it's even better, because we're going to focus on infinite geometric series that the terms of the series get smaller and smaller and smaller. We're going to only focus on, I don't know why I want me to draw. I'm going to only focus on values of r that are between 0 and 1. Because if r was 0, can you imagine? Start with something multiplied by 0, multiplied by 0, multiplied by 0. Not very interesting. Or can you imagine if r was 1? Start with a number, multiply by 1, multiply by 1, multiply. Not very interesting. We're only talking about values of r between 0 and 1. And when you have values of r between 0 and 1, and you raise it to a huge power, you will always get 0. As n goes to infinity, r to the n plus 1 approaches 0. And so all it boils down to is this. Now this should blow your mind. To get the sum of the first n terms, infinitely many terms, of a geometric series, all you need to know is the first term and that factor r. Crazy. All we need to know is the first term and that factor r. 4 divided by 1/2. That series we started with converges to 8. That's what it's all about.